Assalamualaikum warahmatullahi wabarakatuh. Uh, I am from Group 7. Today I will present about our project for course Computer Architecture. Our project topic, which is a single cycle of pipeline CPU by given specification using hardware description language, which known as HDL. Our team members consist of 6 people, which is me, Muhammad Himan. Uh, the second one is Muhammad Afizuddin. The third one Muhammad Shamil, Nabil Zikri, Diva Harun, and the last one is Muhammad Zarfan. For introduction, the design and implementation of central processing units play a crucial role in computer system performance. Two prevalent CPU design techniques, single cycle and pipeline architectures, offer distinct trade-offs. In a single cycle CPU, each instruction executes in one clock cycle, ensuring simplicity but potentially leading to resource inefficiencies. On the other hand, pipeline CPU divide instruction execution into stages, enabling parallel processing and overall performance improvement. So for the result, which I need to create an SR lash. So this is the code for test bench, which is consists of, we need to start with module srff underscore tb, and we need to assign a value which I need to put 6 value from starting from 2, and it will last with 6. For the design, it will make the output from this code. So I need to put one array at the input part, and also the end case I need assign a value which is 2.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Afizuddin bin Azizi. I will continue the presentation about the register. So as you can see here, this is the coding that I use to make the EPWave for register using EDA playground. So the result EPWave is in the next page. So this is the result, the EPWave result for my part, which is register. That's all from me. Thank you.
So, greetings to Dr. Hakimi. My name is Divaran Lakipaniswalvam. I'm a matric at CN 20429. So today, before I begin, I'll be discussing about the creating ALU, which is an arithmetic logic unit. It's basically a crucial component within a processor. A CPU has been on the computer, and just like it derives from the name, it performs arithmetic and logic operations on binary numbers, which are the basic fundamentals of when it comes to computing. So first, we'll be looking at the test bench and also the test bench and also the design. So this is done in the EDA playground. So the test bench is basically a separate set of codes to verify. And the next slide, we will look at the design code, which is the primary HDL code that actually defines the digital design. So the design code basically describes the behavior of the electronic circuit or whatever system that we've been designing. And since we're using Verilog, which is a compiler, this code typically involves modules, signals, and other constructs that actually represents uh, the functionality of that hardware. So first looking at the um, test bench, we're looking at that the module is the test bench for the ALU. So we first have our inputs where we have to give our inputs and then instantiate the ALU module. Then we give different cases where there's bitwise N, bitwise OR, bitwise XOR, bitwise NOR. So we have 8 different tests, and then each test is being inputted the different values that I've inputted. So for example, for test case 3, we have A equals to 8 and B equals to 5, and the output where equals to 3 times with the bitwise N. So we'll display this in the following slides where I show you the waveform. So the next one, the design is what like I said, it's basically to verify the coding. And over here, it is where we give all the case and the mathematical operations that are involved. So there's addition, subtraction, bitwise and bitwise or XOR. For example, modulus and addition, subtraction, all that. So this is what we put in design section of the coding to just to verify the mathematical operations we are planning to introduce in the coding. So the next you can see is the all the values that we have gotten, like the 31 and all the values that inputted, and also all the operations that are involved and the values that we have gotten from it. So on the right side in the blue color highlighted, it's all the outputs, and the left side is all the input. So whether it's addition, subtraction, or thing, you can get it through this output, and it forms a waveform of all the outputs. So next we'll be looking at the state elements on the data part. So we know that in a digital design and computer architecture, a data part basically refers to a portion of processor that actually performs arithmetic and logic operations. So what is state elements? Is basically it's storage elements. It's like flip-flops that store the data of the processor. So by creating state elements of the data part, we involve like introducing storage elements into the data part to store any final results during the execution of the instructions. So the first you can see is the test bench. So for the test bench, you can see that um, we'll get based on the values that we inputted, we'll have the state element where we initialize the beginning, the clock and the test date, and also we initialize the dump file. The dump file is for us to actually have an output. It produces the EP wave for us to see an output of the waveform. Then the next one is our design of the EDA in the EDA playground, where we actually put, like once again, we put all the input elements and all the memory address in order for us to store any kind of information on the processor. And that's the design section is just to verify our coding. So the last one will be the EP wave, and we create state elements on data part. You can see the EP wave, that's the CLK, which is the clock. It is the range from 0 nanoseconds to 100 nanoseconds. Then we have the Q, the test state, the address, and again the clock. And so it's all separated by X1, is by binary and all. So this is the result of the EP wave when it comes to creating state elements on data part.
Assalamualaikum and good afternoon. My name is Muhammad Zarfan bin Alkonso, and today I will present about create data memory units. In single cycle CPU, the data memory unit (DMU) orchestra data transaction between the center unit or CPU and most memory incorporate key element like memory address register MAR and memory data register MDR. The MAR holds the address of the memory location, while the MDR stores the data being read or written. Control logic manage the read or write operation, and data bus facilitates communication notability in a single cycle architecture. Every instruction complete within a single clock cycle, ensuring simplicity in design but potentially sacrificing overall performance compared to the more complex CPU architecture with multi-cycle instruction. So we given task to create the data memories for the single cycle CPU. So here we have the provide Verilog code for consists. So provide Verilog code consists of two modules: data memory and associated test bench. The data memory unit model define a simple data memory with specified depth, mem depth, and interface for reading, writing data. Memory is implemented as an 8-bit array with a configurable depth, and the read operation is controlled by read and signals WR. So the test bench name is the test bench. So instantaneous the data memory unit model for perform series of write reads operations. So the test bench set initial value for the test data address and the write and read control signals simulating the various write operation with different data address. So we set the for the test bench for a delay of 100 times per unit. So the write and read control signal is switched to perform the operation at different addresses. The simulation output is dumped to a VCD file, or we code. The code for is the test.vcd. For the analysis overall, the test pen is designed to verify the correct functionality of the data memory unit by observing its behaviors in response to the write and read cooperation during simulations. Okay, we're going to go to the result of the code of Verilog for great data memory unit. So here we have the result of EP wave. You can see at the left hand side where it shows the address, the data out, the text data, and WR address, data in, data out, and the memdep. So this code, the result where it's simply showing a register array memory to store data, the 8-bit data and output. It based on the output address of when WR is set to 1. So you can see it's set to 1. So it's read, and the testbench set initial value for the test data address and WR and waveform of this input and output data.
Assalamualaikum. My name is Muhammad Shamil, and I will talk about sign extension unit. Okay, what is sign extension unit? Sign extension unit is a component that used in computer architecture that used to extend the sign bit of a binary number to a larger size. Okay, for example, let's say you have a 4-bit sign number, 81101, and you want to extend it to 8 bits. The sign extension will replicate the MSB of that 4 bits, which is 1, replicate the 1 to fill the additional bits that are missing to result to 8 bits, which is 111 11101. Next, we will talk about the coding for the sign extension unit. Yes, for the input, we use signal TB SE in and output signal TB SE out. Okay, and we also use X integer X7FFF, X 8000, and XFFF. Okay, what does this coding do is we will wait for about 100 seconds to change to extend the number to another integer, like from 7 FFF to X 8000 and another X FFF. After that, the process will show that the asset false and the report will end. So the severity is failure. So the coding will end And next we will talk about the EP wave. Okay, this is the EP waveform for the sign extension unit. As you can see that the sign extender component react to an input stimulus, connect signal, TVS out to the component output, so that the integer x 7FFF, x 8000, and x FFF will change uh, depend on the time that had been decided in the coding. Okay, after the simulation ends, it will state that the assert false statement with report end and severity failure is used. When the statement is run, the simulation will end and a message labeled end with the severity failure will appear. Okay, next, I will talk about MUX. Okay, what is MUX? MUX is a multiplexer, which is a digital circuit that select one of the several input signals and direct it to a single output. Okay, this selection input is controlled by a set of binary inputs. Uh, the number select lines determine the number of input channel the MUX can handle. Okay, if we take a look at the test bench and the design, you see that for the test bench we use a module TB. We register one NO, and for the multiplex example, that is I0, I1, I2, I3, and Y. And then for the repeat six begin, that it will randomly uh, make six time of the amount. Okay, if we look at the design, we use module MUX example for the input 1O, and input is I0, I1, I2, I3, and the output is register Y. So that if we look at the case, the case state that 2HOY equal to IO, 2H1Y equals I1, and 2H2Y equal I2, 2H3Y equal I3, and then the coding will end. We end the module. This is the MUX EP wave. We see that the input signal cell I0, I1, I2, and I3 are is the line that instantiates the MUX example module. This also include the MUX example module output signal Y, and also MUX example MUX cell I0, I1, I2, I3, and Y. Uh, This is also sets the input value, iterate the simulation 6 times using random selector values, and display the inputs and output using the monitor statement. That's all from me. Thank you.
Assalamualaikum, my name is Nabi Chikri, and I will explain how to execute the complete MIPS data path. So MIPS is the microprocessor without interlock pipeline stage. It's a type of reduced instruction set computing (RISC) architecture. The data path is a crucial component of a processor that facilitates the movement and manipulation of data between different functional units. So the key components of MIPS is SR latch, SR latch register, ALU arithmetic logic unit, and next is the elements, data memory unit, sign extension unit, and mux multiplexer. And then you can see the text bench, um, the cloud reset, 7 to 0 data, wire memory memory, wire 7 to 0, LER write data, integer, clock cycle, IR types, RPS, SPS, BQS, JSS, and Then the clock pulse duration always 5, and then instantiate the MIPS processor, MIPS, um, CLK, reset, memdata, memory, memwrite, ADR, and raw data. And in the memory, it contains the instruction REC 720, RAM 25520, which equal to 256 times 8 RAM, and then memory, ADR, raw data, and begin. Memory data equal to memory, RAM, ADR, and NSX. If we memwrite data equal to raw data. And on the right side, you can see the design for the main parameter width equal to 8, rank bits equal to 3, input clock reset, input width 120, mem data, output memory and write, and then output again with 120, edit our data. And then you can see the wire 2210, 120, 320, and 220 for their respective integer. And the controller con CLK clock reset instruction 21 to 26, 0 memory right, alias alu, mem IR, and all the means process. And here you can see the result for the DP width. Left side you can see the ADR70, BEQS, CLK, CLK clock, cycles, IS, JS, LBS, M_I 720, memdata 720, memory, memwrite, I 220, reset artifacts, SBS, and write data 720. And then you can see the CLK, memwrite, read and memwrite, and their respective waveform. Another is in binary form. This is our discussion. In this project, we use EDA background to generate digital circuit forms to simplify code editing, simulation, and sharing. EDA background is a free online to focus on small scale design and test bench project, not suitable for extensive FPGA or ASIC projects. This code was crafted for an SR latch operating independently based on S and R inputs. We then created a register for quick memory storage of data and instructions using flip-flops with stem gates. Next, we developed an arithmetic logic unit ALU in the CPU responsible for the arithmetic and logical operations. The ALU directly acts as the CPU controller, main memory, and I/O devices using an instruction word. The state element in the database is a digital circuit storing and retrieving data based on inputs and clock signals. The Verilog code and test bench demonstrate its simple implementation, validating behavior. Overall, EDA Playground simplifies digital circuit development, and the state element is crucial for storing data in circuit.
I will continue with conclusion. So in summary, the assembly of essential components such as instruction memory, register file, and arithmetic logic unit ALU is vital for constructing the fetch or execute cycle in a MIPS processor using Verilog. The provided Verilog code demonstrates a concise single cycle MIPS processor design where each instruction is executed within a single clock cycle. The CPU retrieves instructions from memory, decodes them to extract register and opcode details, utilize the ALU to perform the operation, and then resets the program counter for the next instruction. While this example imparts a fundamental understanding, a more realistic implementation would entail incorporating additional components supporting diverse instruction types and addressing various control signals and hazards. Despite the increased complexity introduced by pipeline or multi-cycle architecture in processor design, the concept outlined here serves as a groundwork for comprehending the fundamental principle of mixed processor implementation in Verilog. That's all from me. Thank you.